I remember we discussed a little bit about this problem, but let us forget about it and start from scratch once again. So forget about my translation or whatever, but the point is that we have a sphere. This is a candle, spherical candle. The first volume, the initial volume, these are the important things, is given to be 3 cubic centimeter. And then, so this volume is shrinking when you burn the candle or whatever. I am just making stories. I don't understand what's written here, okay? Anyway, but then after t, so the time is in month, and we know that after 1 month, the volume reduces to 2 cubic centimeter. But the essential phrase is this proportional. They have mentioned that this decrease in volume is in a way that the rate at which this happens is proportional to the area of the sphere or of the candle. So is that clear? So if I want to explain, so let us say I have a sphere, this sphere shrinks, but the rate at which it shrinks is in a way that the rate at which the volume is changing is proportional to the area of the sphere at that time. Okay? Is that clear? Yes or no? Hello, are you with me? Yes. Okay, so what does it mean? Let me read the question here. So the initial volume, so let me write V0 means the initial volume. The volume when we start investigating this process is 3 cubic centimeter. After 1 month, the volume V of 1 is 2 cubic centimeter. This shows that the volume is changing over time. They are saying that the rate at which the volume changes over time is proportional. If I can draw this symbol, this is proportionality symbol, is proportional to the area of the sphere. Okay? The first part of the question asks you to prove that the rate at which the radius, which they denote by little r, is a constant. And of course they have written the constant to be k, but anyway, we want to prove that the rate at which the radius is changing is a constant. Do you think this constant is positive or negative, even without the calculations? Is this constant positive or negative? No, you don't need to read. Is this constant positive or negative? No, why positive?
Because the decrease in the radius.
Yes, the radius is decreasing, yes? So this should be negative. Over time, r is shrinking. So definitely this constant should be negative. You don't need to read the problem again. Okay, so the first thing we want to show, according to this assumption, that the rate at which the volume is changing is proportional to the area of the sphere, we want to prove that the rate at which the radius is changing is a constant. And the second question is interesting. We want to find the volume after 4 months. This is the question. Okay. This is a good problem. I mean, you see that this is a national exam problem. Let us concentrate on doing the first part together. So how can I prove the first part? What I need from the formula sheet, apparently you need 2 things. You need the formula for the volume of the sphere, and because the area is also involved, you also need the formula for the area. So let me write them. So if you go to formula sheet, then you will find this formula for the volume of the sphere with radius r, and then you will find this formula for the area of the sphere of radius r. So these formulas, you read them from the formula sheet. Okay, do you remember what was the way we solved these problems? We think about three quantities. Quantity V is the volume. Of course, it depends to quantity R according to this formula. But in this problem, R is not fixed. R is changing over time. So R also depends on time. Okay? What is the meaning of proportional? When I say two quantities are proportional, for example, let me say alpha is proportional to beta. What do I mean? Yes?
Which means there exists some natural number, okay, let's say, which when multiplied with b gets a... Or
Not natural, a constant number.
okay, constant.
Yes? So it means when I say alpha is proportional to beta, it means if I double beta, alpha doubles. If I triple beta, alpha triples, yes? So that is the meaning. When I say alpha is proportional to beta, it means alpha is a constant, which we don't know, multiplied by beta. Okay? So when I say dV, dt is proportional to A, what does it mean? It means there exists a constant. So this symbol means there exists, yes? There exists a constant in R, if you want to, because we don't know what that number is, so that dV dt is k times A. Okay, let me wait. Do you understand what I have done? This Swedish sentence in mathematical notation can be written in that way, but this is not a good symbol to work with. Equality is better, so I translate this to equality sign. This is what I know. Okay? But now, I want to know something about dV dt. V is my first quantity, T is the last quantity, so we learned about. I want to know dV dt. We learned this is dV dr. The derivative of the first quantity with respect to the last is the derivative of the first quantity with respect to the middle one multiplied by the derivative of the middle one with respect to the last one. That is the chain rule. Okay? Now, instead of this one, what can I write? I can write k times A. Instead of dr dt, I don't have anything to put in. I want to derive something for it. So my duty will be to simplify this. What is that? I see the formula. I want to differentiate V if R is variable. And that is extremely simple then, yes? So dV dr is what?
4 pi r squared.
Yes, because I have 4 over 3. 3 goes down, which cancel this 3. It becomes 4. And then I have pi r squared. And suddenly, 4 pi r squared is A. So this becomes A again. So I put this here. So if you ask me what is dV dr, I will answer you this is the area. So instead of dV dr, I put the area. Yes? And now I can cancel out the area. So I cancel out this area with that area. What do I get? I get K is equal to dr dt. But what was K? K was a constant, so I achieved the goal. I was able to show that dr dt is equal to K, which is a constant. So it means dr dt is a constant. Yes? So that part of the problem, the algebra was extremely simple, but you have to be able to translate it into mathematical language properly. But I want to wait for you to ask your opinion. What do you think I can do to find the volume after 4 months? I know the volume, initial volume is this, and I know that if I wait 1 month, the volume is this. Now the question is that, based on these conditions, if I wait 4 months, what will be the volume? Okay, do you have any idea how to continue? Hmm?
The first idea that I thought of was that we find the radius at V0 and V1. So then we can find the rate that the radius changes. It's a constant.
Yeah, the idea is correct, but how can you find the radius?
We take the volume, so 3 centimeters cubed, and then we reverse engineer the volume formula to.
Yeah, you can find R. Yes, that is easy part. I agree with you. So you put this. If I understood you correctly, you put this here, you find one R. You put this here, you find another R.
Yes.
That is correct, and that is needed. But then, what do you do with that data?
Find the difference to find that the rate changed each month, and then use continue subtracting by the same rate until you get V4.
Okay. Yeah, understandable. But this is working in this problem quite fine. And the reason is that the rate at which the radius is changing is constant. But if it was not constant,
Then
it will not work. But how it works? So let us follow the general rule. So if you write this for this problem in this, that's completely okay. Because the rate at which the radius is changing is constant. But let us say it is not constant, it is t, for example. Then what do you do? So this is why I want to follow the general route here, okay? What do you do there? It's very simple, exactly what you described for a constant, what should I do in general? This tells you that derivative of r with respect to time is constant. So can I say something about the function r? The function r is a function so that when I differentiate it, it becomes k. It's a first degree equation. It's a first degree polynomial in time. So from here, you can understand that if I ask you, give me a function whose derivative with respect to time is k, one of those functions is k times t. Do you agree? But this is not the whole story, because I need the most general solution. What is the most general solution? I have another constant n at the end. Yes? So this is the most general solution to this. If I ask you what r is, this is the answer. By the way, we studied a little bit about this in Math 3C. What is a primitive function for k? What is a primitive function for 5? Answer in x, because in Math 3C we worked with x. What is a primitive function for 5? It's 5x plus a constant. So that's exactly the same story, but here t is playing the role of x. Okay, so that's it. And then exactly what you just said. So what I said, you see I have 2 degrees of freedom, k and m. I have to fix them. And this is why I have been provided with 2 pieces of information to be able to fix them. But as you said, this is constrained on v, but this is constrained on r. So from these 2, exactly as you described, I find r. Okay? So what I do, I would say that v at time 0, according to the formula of the volume of the sphere, is this r to the power of 3, but at time 0. This number is given to me, which is 3, is equal to 4 pi over 3 r 0 to the power of 3. Okay, so I multiply, divide, take the third root. It gives me r0. I multiply by 3, it becomes 9 over 4 pi, and then I take the third root, centimeters, yes? This is r at 0. But again, I write the same formula for 1 month. So v at 1 is equal to 4 over 3 pi r at 1 to power 3. Yes? But this v is also given, which is 2. So it is 4 pi over 3, and then I have r1 to the power of 3. So again, I multiply by 3, divide by 4 pi, take the third root. So r of 1 becomes the third root of 6 over 4 pi. I intentionally didn't simplify that, of course. Let us keep to it. Of course, if you don't like working with numbers, you can just put this in the calculator directly and work with those numbers. But I am obsessed with precision, so let us continue with precise values. Okay, but these are R0 and R1. These two will help me to find K and M. How? Okay, simple. Here, R of 0 is this number. Okay, R of 0 is this number. On the other hand, R of 0 is M. So they have to be equal. Yes? So this is everyone following or not? So R of 0 on the one hand is this. On the other hand can be calculated by putting 0 here, which is M. These two values should match. So I found my M. Yes? And the next thing is R1 should be this number. So R1 is equal to this number on the one hand. What is it on the other hand? I have to go here and replace T with 1. When I replace it with 1, it becomes K plus M. Yes? Okay, but can I find K? Yes, because I already found M. I know what is the sum, so I can find K. So K becomes this number, whatever it is, minus M, which is this number. Was our prediction correct? Is K negative? Yes. Because the denominators are the same, the third roots are the same. This is 6, this is 9. So it is negative, as we predicted. Okay, so that is my K. I don't know if we can make it more beautiful. I doubt a little bit. Well, we can factor the third root. This is just decoration, you know. If you don't like it, you can just put the number in the calculator. So I am factoring 3 and 4 pi out. What is left for me? The third root of 2 minus the third root of 3. This is my K. Yes? And then I have my R. So R of T becomes finally, instead of K, I have to put this number. So the third root of 3 over 4 pi. And then I have the third root of 2 minus the third root of 3 multiplied by T plus M. What is M? The third root of 9 over 4 pi. So this is finally my R. Okay, if I want to test, are you with me or not? What is the next step? The question is, what is V4? So what should I do?
Put 4.
Put 4, it gives me the radius after 4 months. Okay? So R of 4 is the radius after 4 months. I don't know if it's a good idea to keep this obsession with precise values, but I mean, if you don't like it, I know you don't like it mostly, you just put it in the calculator. And then I put 4 here, and then I have this number. So this is RT. Do you have any suggestion to make it more beautiful? I think we can also factor this out. Yes? So let me just do that. So I will take the third root of 3 over 4 pi completely out. This is left for me. This is left for me times 4. So I'm pulling this out. This is left. And that is, what is left from there? Can you tell me? I put this out. The third root of? 3. Unfortunately, we suffered in vain. Yeah, a little bit more, yes. A little bit more. I don't think we can come to abstract beauty here. But let us just do that. By the way, don't let this distract you. The problem is extremely simple. Just put it in calculator. That's a number, okay? But I told you I want to see what is happening. This is just a curiosity. So I multiply 4 here. Yes? And I also multiply 4 here. Then I have 1 here, so it becomes minus 3. I cannot do better than that.
So
This is the radius.
did the first when they got this assignment during the national test, were they allowed to use a calculator?
Yes. That is extra. But that's what I'm saying. Don't let this distract you, because if you don't like precision, of course, you really don't need to bother in the national exam. You just put this in the calculator and find. The reason that I don't like it, why do you think? There is a practical reason I don't like it. Why? Do you understand why? Yes?
I mean, then you can suddenly get different answers depending on how you round, which is kind of...
Yes, more practically. If I want to start rounding in the middle, I am accumulating the errors over and over. I mean, for the exam and this course, it doesn't matter. But I want you to understand, if I give this to GeoGebra by the program, how it's programmed, it takes care of the error here. But this will be done in one go. But if I just do this in my calculator, keep some decimal points, do this in my decimal points, do this in some decimal points, I am making error every approximation, and I am accumulating all those errors. So the error becomes bigger. Okay, so there is something why I'm doing it, but at the level of your lesson it is not important. If it is given in the exam, just put it in the calculator if you are more comfortable. Anyway, this is my R4, but I don't need R4, I need V4. But that's an extremely simple step to take, yes? So V4 is what? Is 4 pi over 3 multiplied by R at time 4 to the power of 3. Yes? And the good news is that at least I can get rid of that part. Yes? Because this becomes, it becomes a little bit beautiful, you know. When I raise it to power 3, this is 3 over pi over 4 pi, which is cancelled by that one. And then unfortunately I have to live with it. So this becomes 4 the third root of 3 minus 3 third root of 3 to the power of 3. And this one and that one are totally gone. So this is my exact answer. But you know that mathematicians are obsessed with precisions, but to be honest, this is not a good number for any practical reasons, yes? Because you don't have a feeling about what that number is. If you want to get a feeling, you have to be engineer. So then you have to put this in the calculator to see.
Is the third root of 2 and 3 are those irrational numbers?
Yeah, they are definitely irrational numbers. And the proof is not hard, I think. Okay, let me put this in GeoGebra to see finally if we can get the correct answer or not. Okay, so in GeoGebra, if I have done everything right, so I need to calculate that number. So I open a pair of brackets, and I have 4 times. The third root symbol is here. So I take this one, I put 3 up there, and then I have 2, and then I come out minus 3, I put times, and then I go here, the third root of 3, and then to the power of 3. Okay, this is the, can you check the faucet if this answer is correct? Where is my book? Yeah, so the answer is correct. But I told you that it is much simpler than it looks like. The reason that you might become a little bit freaked out is because I am keeping these exact numbers with myself until the very end. Okay? But you don't have to. For this exam, for this, you just immediately calculate these numbers in the middle of the way. Okay. Any questions? So that was one of the good questions, I think, in the book. Let us go to see if we have other choices to. We learned before, yesterday. Is there something interesting we can find here? Okay, so 2 interesting things I found here. This you can consider it part of the lesson. Do you remember? Let us think about these two problems. The problem, if you remember, we didn't prove this limit, but we told that if x is measured in radians, this limit is, do you remember? No, this left one is 1, the right one is 0. If x is expressed in radians. But here, this is telling you that x is measured in degrees, and then we want to know what the answer is. This one we want to prove. Okay? We take the radian one for granted, and using that we want to prove what will happen if x is measured in degrees. Okay, so let us try to solve it together. I want to ask your opinion about it. And I don't know, I want to put the degree sign. I want to see how you think about the problem. You see, let me tell you. Yesterday, we learned that the limit of sine h over h, when h goes to 0, becomes 1 if h is in radians. Okay? Using this, we want to answer this question today. What happens if I have the limit of x over x when x goes to 0 if x is measured in degrees? But I think, might be some of you don't like it. I don't know, Rasmus, might be you don't like it. But I want to put the degree sign here. If I want to put the degree sign here, where do you put it? Because that I think it is essential to solve this problem. I want to take, so you know that x is measured in degrees. So if I want to make it explicit, I want to put the degree sign somewhere. Okay, where I should put it?
Either
No.
for it to be the same value as in radians.
No. They are telling you, they have mentioned it in words that x is in degrees. But I want to, x is in degrees, and I want to make it explicit by putting the degree sign. Should I put the degree sign here? Should I put the degree sign here? Should I put both of them? Because answering this question will help me to describe it better and simpler. Yes, what is your opinion? No, just tell me.
My opinion would be that it should already be within the value of x. But if you want to say that the value of x doesn't have a degree sign package in it, then I would say just the x within the sign.
Within the sign. So what you are saying is that put the degree sign just within the sign. Okay. Do you think this is good, or do you think this is good? Because Rasmus is saying this one. Yes?
If you put a degree sign on the bottom one, then you're dividing, because sine of x is a degree, then it's a number.
It's a number, exactly. So what Rasmus said is correct. So if you want to make it explicit, you shouldn't put it here and there. You have to put it only on top. Yes? Okay. Now, let us continue. Do you remember what was 1 degree in radians? Even if you don't remember, you visualize. What is 1 degree? You need to remember the full circle is 2 pi. So you divide it by 360. So it is pi over 180 radians. Okay? But x degrees becomes what?
X times.
What should I write?
X times pi over.
X times, exactly. So without the degree sign, yes? This is x degrees. So let us put it here. So this becomes the limit of sine. Instead of x degrees, I put this much radians. And then I have to write x. X goes to 0. Okay? But can you tell me how can I calculate this? I want to prove it. I am taking this for granted, but I want to prove this. So how do you think I will do? it is not exactly this combination, because this combination tells you sine of an angle divided by the same angle when the size of the angle goes to 0. This combination is not exactly that one. It is sine of an angle, but unfortunately it is not divided by the angle, because the whole angle is this guy.
But what is x then? X is just number.
No, x is an angle, for example, okay? But the problem is that if you want to have it 1, these two should be identical. In my case, these two are not the same. One of them is this, the other one is this. Okay? So what do you think I will do now? I introduce a new variable. I would say let h be defined to be pi x over 180. Okay? What is the benefit of that? First of all, this h is in radians because it was in radians. So this becomes the limit. In the numerator, I can write sine h radians. But instead of x, what can I write? I can write 100 times h divided by pi. So if you don't mind, let me write 100 times h divided by pi. That is what after substitution. But here x goes to 0, it implies that h also goes to 0. Because if x goes to 0, pi times that also goes to 0. But now what happens, this comes up, it becomes the limit of pi over 180 times sine h over h when h goes to 0, but that is a constant, I can pull it out of the limit. It becomes the limit of sine h over h goes to 0. But this h is exactly in radians, and that limit is 1. So this becomes pi over 180 times 1, which is pi over 180. So this limit is pi over 180. Oh, sorry, not degree, pi over 180. And this is why it is beneficial to work in radians if you want to work with derivatives. Otherwise, we have to carry this unfortunate constant with us. Okay? So let me make it more clear to you. First of all, tell me, do you understand what is going on? In the book, the answer is not this. That is stupid. They have given you the approximate value. Why should we do that? I mean, let me just do this. So pi, do I have pi on iPhone? Okay, yes, pi divided by, pi is 3.14 something. I divide it by 180. Yes, the answer in the book is 0. That's, I don't know why. You know, the people who have written the book are not mathematicians, they are engineers. Because all the book is filled with these kind of numbers. Okay, so anyway, this is not, it's just, the answer in the book is this number, I think, or only 2 decimal points, but the exact value is this, and that is pi over 180. So you now, hopefully, Simon, you agree with me that this doesn't remain the same. But for the next one, if you don't mind, I don't want to prove it for you, it doesn't change, yes? Yes?
I mean, this might just be a coincidence or random observation, but the fact that 1 degree is equal to pi over 180 radians, and if you calculate these two, you get 180.
Yeah, something like that, yes, because you see that, yes? Yeah. Okay, so it is, let me finish this problem, then we can discuss, okay? So the other problem, so hopefully you agree with me. So now if you don't like it, Rasmus, I can clean it, okay? But anyway, so this is in degrees. And this is in radians. Okay? Now, do you remember we had also this before yesterday? Cosine h minus 1 over h in radians. If you remember, I tried to motivate you exactly the way the book did. It is 0. Now my question is that if now it is expressed in degrees, what do you think will happen now? This is in radians. Okay, we didn't prove this, by the way, but we convinced ourselves. And then in degrees. Now my question is that what do you think will be the answer? This time it doesn't change. Yes?
Yeah, right.
Yeah, because the value is 0. It doesn't matter if you change the unit. It would be very strange if I have a length of 1 meter, if I change to feet or I don't know yard, then suddenly it becomes 0. It doesn't work, yes? So yeah, you can convince yourself. Don't take my words for granted. Try to do similar thing. Okay? You will learn. Okay, let us do it in our head. Instead of x, I put this number. Okay? But this factor that came up still will come up, but will be multiplied by 0. So the answer will be 0.
Also, honestly, at this point, I think you convinced me that it's better to write it in degree sign. Because otherwise, we have like leftover stray per degree.
Yeah. No, I think so. I thought a lot actually, but then I think that because this problem is confusing for some students, because when they say x is expressed in degrees, that is the common mistake. They consider both of them in degrees. But as far as you understand that is not the case, that's okay. Okay, now let us, if you don't mind, let us go back. No, let us do it like this. I want to ask your prediction about the formula for the derivative if x is expressed in degrees, and then we see that it conforms with what we have learned here. My question is that if I give you f of x, so x, so let me start with the sign. So do you remember yesterday I told you that the derivative of sine is what? Cosine, but x is expressed in radians. Now can you predict what will happen? We can in two different ways. One, using these new numbers. Once in a different way. What will be the derivative if x is expressed in radian? In degrees.
Shouldn't it be 180 cosine?
Yes, that becomes that one. Why? Because do you remember the way that I did it yesterday was to write the formula. So this is the limit of f of x plus h and then minus f of x. So let me just do it quickly. H goes to 0, and then I wrote this limit of sine of x plus x degrees plus h degrees. So x plus h in degrees in principle. But that means the same thing, okay? Minus sine of x degrees and then divided by h. H goes to 0, okay? And then when I open it up and factor it out, this becomes this limit. If I remember it correctly, this becomes cosine of x degrees, and then it becomes sine of h degrees divided by h. H goes to 0, and then plus. I open it up exactly as before, okay? And then the answer that I get here is sine x degrees, and then I will have cosine h degrees minus 1 over h. This is what I will get. Exactly as I did before for radians. But this time what will happen? This is still 0, even in degrees, but this one is no longer equal to 1. It's pi over 180. So as Oscar told us correctly, the answer will be this times that, and this one is 0. So you see, I hope that you agree with me that it is better to work in radians. Otherwise, we have to carry this ugly constant with us all the time. Okay, so but it is possible. So the derivative, if I want to answer this question mark, the question mark becomes pi over 180 cosine x in degrees. Now, I want to test your understanding. Could you do it a different way now? Without the limit idea. Yes? So, what other way we can do it? Yes?
Couldn't you substitute x for, was it pi over 180 and then use the chain rule?
Chain rule. Exactly. That is exactly what I was. So you don't need to suffer that much. So you just take it. So you say that f of x, instead of sine x degree, what do I write? I write sine, it should work, yes? Sine of pi over 180 times x. Yes. Yes.
Why?
X degree should be the other way around, is it? Okay, let us go to the other room, we can do that. We know the formula, so we learned that if f of x is sine x, the derivative is cosine x in radians. Okay? This is the one that you really need. Don't worry about this problem. This problem is just an exercise to see what happens if you work in degrees. But this is the only one you need. Right? But if I have this function, g of x, which is sine x in degrees, then using the same method and using the what we learned in the previous classroom, what is the derivative here? It gives me a little bit of problems with putting a factor in front of it. But other than that, it works. But my impression was that we should be able to also extract the same information using the chain rule. Yes, aren't we?
I mean, you just say that
Because x,
if you convert x to degree from degrees to radians, then you get the coefficient pi over 180.
yes, so it works.
Yeah.
So instead of x degrees, we write x times pi x over. So let us write like this. I want to calculate the derivative of sine when x is measured in degrees. Instead of x degrees, I write pi x over 180 radians and then take the derivative. But this now considered to be u, this is sine u prime in the radian mode. The derivative of sine is cosine, but it is not finished. We have to multiply by the derivative of u as well. Yes? But now switch back. If I take the derivative here, what the answer is? What is the answer to the derivative here? Pi over 180 is constant. The derivative of x is 1. So it becomes pi over 180. And then, of course, I can keep it like this. But because my problem is in degrees, it is better to switch back to degrees again. So this means that this becomes x degrees. So this is two perspectives of, this is good, you know. If you don't have those subtleties, if you still want to discover the formula of the derivative in degree mode, you don't have to go through the limit part and everything. It is just simple as that, and you get this answer. And I think the same factor will, according to this, the same factor will appear for the derivative of cosine in the degree mode. But of course, because the derivative of cosine is minus sine, it becomes minus. Okay, so I think it's enough. At least we have a good understanding of what is going on if you are not working in degrees.
You said, yeah, because if you, because this is, but if you take like the second derivative of sine, then you'd have to add another factor of that, so it would become like pi.
Yes, pi. So it is. Yeah, that is good. That is good to see. I mean, you might live with it. Yes, but if you want to do another derivative, then another factor of pi over 100 will go out, and then it becomes bigger and bigger. So this is beneficial to really work in radians. Okay, at least one idea of why we work in radians. Okay, the next question below this question, which I don't know why it is level 3 problem, but anyway, the next question is the derivative of this one. I want to wait for you, okay? So I don't have pause option in this. These applications are crazy. I don't know what happens if you just put the pause button there, yes? They force you to buy another application. Anyway, so y is equal to 1 over sine x. I don't know, to be honest, why this is level 3 problem. But anyway, you want to find the derivative. And I will write the number of question right now. Where is it? This question is 3216. 3216. Of course, they haven't given y, they have given f of x.
Should we differentiate this?
Yes, the question is, what is the derivative?
And this isn't in degrees or anything.
Pardon?
This isn't in degrees or anything.
No, this is again back to normal situation. We always work in radians unless explicitly mentioned otherwise.
Nej, för du... Ja, derivaten av negativ tangent. Du derivaten av 1 inom x. Nej, just det. Nej, men så skriva om.
The reason I think they ask you to do this, because this combination, I gave you the name. Do you remember this? This is not in Swedish system, but 1 over sine has another name in trigonometry. It is called cosecant. Okay, and then you want to see what the derivative, because it is important. When you go to university, there are a lot of integration that you need to do, so it is better to know the derivative of cosecant. But here you don't need to be worried about that. But what is your suggestion for me? Because we haven't still studied the quotient rule. The next lesson will be the quotient rule. If I had told you this, you could use that here, but we don't have it. So it is better to do it in a different way. Yes?
Using this logic of using a u, I guess, because in our table we don't have exactly this, but we have 1 over x. And
exactly. So that is chain rule. Yeah. Yes? So what we do, is it a good option to take this u? Let us check. When I take it u, then I will have this function. This function is comparable to which function? 1 over x. Do I know the derivative of 1 over x? Yes. If you have it in your memory, write it down. If no, you check it out. What is the derivative of 1 over x if you don't remember it? Bring x up and take the derivative. Minus 1 goes down, x to the power of minus 2. Simplify it, it becomes this. Okay, so the answer is this. Anyway, I was able to do this. For this one, what will be the answer? The answer for the u1 will be exactly as if u is x, means this. But you have to multiply by u prime. That's the only difference. So I will do this. So if I ask you what the derivative is, the derivative f prime is equal to minus 1 over u squared. U squared is sine squared. And then times u prime. Yes? And then what happens? This is the copy-paste part. So I haven't written the formula, but hopefully you remember. The derivative of sine is cosine. In this problem, if you stop here is okay. I prefer to put it up there. That is also okay. And this is what you expect to write here. But let me also tell you the university part. Can you write it back in terms of cosecant? It's not necessary. This is the end of the solution. So let us say that you go to university and learn that this is called cosecant x. So this exercise is teaching you how to find the derivative of cosecant x. So I found that the derivative of cosecant x is equal to this guy.
You can factorize the cosecant.
Yeah, so what they do in university, they write it in a slightly different form. They write it as cosine x over sine x multiplied by another 1 over sine x. Yes? This is exactly cosecant again. And this, I don't know, do you remember this one? It is opposite, it is the reciprocal of the tangent. And that is called cotangent. So it becomes it. So yes, in university, this is the formula that you have it in the formula sheet. This one is minus cosecant x, cotangent x. This orange one is not necessary for you to know. And then you can similarly show that if you have secant, it becomes secant tangent. But what was secant? Secant was 1 over cosine. Okay, so you don't need to learn this orange one, but it's help. Yes.
So the cotangent is also secant over cosecant, or cosecant over secant, or
Yeah, you can.
yeah, well, I guess that makes sense because
Yes, because this goes to the denominator, that goes off. Yes. Okay, but let me solve one national exam problem here. That is problem. It's a very simple problem. Okay, 3211. So 3211. It's a national exam problem, 1997. Okay, so we want to find f of x plus f double prime of x. This is wanted if the function f of x is 4 sine 3x minus 5 cosine x. Yes? I think, even though I don't have a pause button there, but we wait.
And we don't have just the expression for this.
Yes, they have asked you the same. I don't know, might be it becomes a number or might be it becomes a function, but what they want you to answer this. Okay, I can stop and then glue them. I think this is not hard. Let us just do it. Do you think I really need to do every part? So what should I do? I take this derivative minus that derivative. This is a constant, so I don't care. Okay, let me write it in 2 steps. And then I would write this. Yes? This one is extremely simple. You just go to the table, the formula is there. The derivative of cosine is negative sine. So this becomes positive 5 sine. But what about this one? The derivative of sine of u is cosine of u, which is cosine of 3x. But let us do it in our head. You have to multiply by u prime. What is u prime? 3, and you have another 4 here, so it becomes 12. Do you agree? Any questions here? So the derivative of sine of u is not just simply cosine u. You have to multiply by u prime. Okay, so I take f double prime of x. So what is the derivative of sine? It is the simplest one, so let us just do that one first. It becomes simply cosine. But what is the derivative of this part? 12. The derivative of cosine is negative sine, but that is for x. This is not x, this is 3x. So I have to multiply by the derivative of 3x, which is 3. So let me simplify things a little bit. 3 times negative sine times 12 is minus 36 sine 3x plus 5 cosine x. This is my second derivative. This is my function itself. The question mark is function plus the second derivative. And then I have to do some simplifications. Okay, what do I get a number at the end or not?
No, you just get
It becomes
I get
anything is one thing should be simplified. So let us see. The question mark is f of x, which is 4 sine 3x minus 5 cosine x, and then plus the second derivative. So the second derivative starts with the minus, so it becomes minus 36 sine 3x, and then plus 5 cosine x. Of course, this one and that one are simplified, but not more than that. So it becomes what? Okay. So if you got this answer right, it means that you are on the safe side. I mean, this is a national exam problem. You know? Is that clear? Okay, I don't see any interesting problems, you know? No, there is nothing. So let us go to the logarithmic derivative. But the problems are extremely simple. There was just one nice problem and we solved that yesterday. Okay. So for example, let us take this derivative. This is problem 3224. 3224 part C. The function is this function. Y is it is very simple. It doesn't make any problems. We want to differentiate this function. What is y prime? E to power 2x minus 2. And let me also write one problem. If you can solve this problem, it means that you are really on the safe side from the chain rule point of view. So this, let me write it myself. So what is the derivative of 5 sine to the power of 3, and then you have the square root of x squared plus 1. Okay? Yes. If you really can take the derivative of this function, so do you, I want to read it right, yes? Sine of this angle, whatever it is, raised to power 3 and multiplied by 5. So in principle, I don't need to exaggerate so much. But I want you to know this power of 3 is not the third root, is the power on top of this one. So if you really can solve this problem, it means that you really learned everything necessary for the chain rule, up to differentiation, because there are some conceptual questions. And I already, by the way, I put 2 videos for interested students. They are short videos about the chain rule, about differentiation. Whenever you have time, check it out. Yeah, on Google Classroom, you see the lecture, video lecture, but you also see some short videos. Yeah, don't see the solutions, try to do them yourself first. I can stop. Finish this one. You will not definitely get something like this in the exam, but it is not beyond what you can do. You want to differentiate a function. I'm lazy to write a table there, but you know that. Okay, so the first thing is that this is not directly your table. No, first of all, this 5 is not important because it's a multiplicative constant, so I take it out and then I concentrate here. So 5 is already there, yes? But then I have to take something u to be u. I have some alternatives here. You might think that this is u. Some of you might think that this is a good choice for you. Some of you finally might think that this is a good choice for you. Which one is a good choice? For example, this one is not a good choice because if I do that, it becomes this. This is comparable to what? But is this in my table? No. So this means that this is not a good choice for you. Is the next one a good choice for you? Again, no. Because if I take the whole thing to be u, then I will have this. And this is comparable to this. Do I have this in my table? No. So none of these choices is good. Then there is only one choice left. I take this to be u. Is this one good? The answer is yes. Why? Because then what happens? My function becomes 5u. Let me write it as usual. It becomes 5u to the 3. This function is comparable to 5x to the power of 3. Do I know the derivative of this? Yes, it is 15x squared. So what will be this derivative? It follows the same rule as if u is x, but you have to multiply by u. You see, I am repeating the same process over and over again, even if the problem is harder. So y prime becomes equal to 15 u to power 2, which is sine square root of x squared plus 1 to the power of 2, but multiplied by u prime. Yes? Okay, this is the copy-paste part. I have to concentrate on the prime one. So again, I have to take something u because this not in this form is not in my table. Again, you can process. Is it a good choice to take this u? No. So the choice of u would be this one this time. Is it a good choice? Yes, because I will have sine u if I take this u. It is comparable to sine x, and sine x is in my table. The answer is cosine x. So this means that this also becomes cosine u, but multiplied by u prime. So instead of this, I write cosine u, but multiplied by u prime. The problem is still not finished because prime is still left. But now this time I will take this to be u. Is it a good choice? Yes, because it becomes the square root of u. The square root of u is comparable to square root of x. The derivative of this, I have it in my table or in my memory. So this becomes exactly the same thing, but by multiplying by u prime. So this means that I copy and paste everything so far. It becomes 1 over 2 square root of u. It is not finished. I have to multiply by this. Now I hope that you appreciate the name is a good name. This is like the chain, yes? And then finally, what happens? The last one is extremely simple. It's just 2x. But because it is so simple, it becomes 2x. The 2 that I get from here and these 2 in the denominator will cancel out. There will be 1x. If you don't mind, let me write it here. So it becomes 15x sine to the power of 2 square root of x squared plus 1. And then I have cosine square root of x squared plus 1. And then divided by square root of x squared plus 1. And that is my derivative. So we have to use the chain rule how many times? Once, 2, and 3. Yes, I mean, Oh, 4 times. Yes. Yes.
I think you can simplify this a bit more, but it's kind of you can.
No,
but
It's
can't
not
change.
simplify. You can
Well,
put
you
one
can.
sine with cosine and use double angle formula, but it is not that simpler. If you want, we can write
you
it
can
like
do
that.
it with only sine.
X, and then it becomes sine 2 square root of x squared plus 1. Yes.
and the times.
And there is another sign left, unfortunately.
Yeah.
So it's not that simpler, yes. Then I have to put the 2 also here.
Yes.
Yeah, I don't think it is more beautiful. I think.
Well, there's only one sine. There's only sine at least.
Yes. Anyway, but I mean, if you really could do this yourself, you really learn whatever it is needed for the chain rule, except those conceptual questions. I mean, do you remember we had some graph ones that we have to use the information on the graph to solve those problems? Those are conceptual problems, but this is the technical problem. Okay, any questions?